Good evening, ma'am. Today's topic for our nature-inspired computing AAT is PSO, which stands for Particle Swarm Optimization. This AAT is presented to you by me, Virat, my teammates Vishruth and Yashaswini. So the first is the introduction of PSO. So PSO is basically a search method which is introduced by Kennedy and Eberhard. It is an idea which comes by observing how a group of birds or fish coordinate their movement to find favorable locations. These favorable locations are mainly targeted for areas which are rich in food. And in PSO, this behavior is basically simulated by having particles which move through a specific space while exchanging insights about how their position has strong mechanisms which they can learn from. And through the shared learning, the entire swarm is guided towards high quality solutions. So this basically makes a PSO very powerful approach for tackling optimization techniques. It is a widely used method because it is very easy to implement. It reaches very good solution quite easily and quickly as well. And it works well with very difficult non-linear or high dimensional problems which other methods are not able to solve. This method also does not rely on any gradient details, which also allows it to be functional, uh, which used to be on functions which cannot be differentiated normally. It's a mix of basically broad search and focused refinement, which helps it to explore very large solution spaces effectively. It is applied in fields such as machine learning, engineering design, scheduling, clustering, and many other practicals. So the natural inspiration behind PSO is how birds and fishes basically group together, but they also search individually. And if one of them finds like a food source or something which is valuable, the other birds observe it and they move in the same direction as the first bird which found it in the first place. And this basically gives them a shared and adaptive behavior, and it allows the entire flock to reach the most rewarding regions efficiently as everyone works towards like having a common goal and they share all the details they find in between them. This applies for all the optimization techniques which we use inside the model. Next is the algorithm. The algorithm basically consists of the first step being as initialization. This initialization is defining the objective function which has to be minimized or maximized. Then after that we find the algorithm parameters which consist of the swarm size, the maximum number of iterations that the swarm will go through, the inertia weight, the cognitive coefficient and the social coefficient. Then after the third step inside the initialization will be the to initialize each particle with a random position within the search space and assign them a random velocity and also provide them with a random personal best value which will be appropriate to their initial position. Then we said the global best value among all the personal best positions. Next will be the fitness evaluation. So for fitness evaluation for each particle, we find it by evaluating the objective function fx. Then we compare the current fitness with the particle's personal best fitness. And if the current fitness is better, we update the particle's personal best position. The third one will be updating the global best. Among all the updated personal values, we identify which particle has the best fitness and assign it any position which will be assigned as the global best or G best. Next will be the velocity update. It is given by the following formula, which is Vt plus 1 equals to W into V1 Vit plus C1 R1 inside bracket P best I minus XIT plus C2 R2 inside bracket G best minus XIT, in which VIT is the current velocity of particle I, XI is the current position of the particle I, P best is the personal best position found by the particle, G best is the best position found by the entire swarm, and R1 and R2 are just random weights inside 0 to 1 variable. W is the inertia weight, C1 is the cognitive factor, and C2 is the social factor. Next is the position update. So after updating all the velocities, we find it by xi equals to t plus 1 equals to xi t plus vi t1 t plus 1. If the new position goes out of the search boundaries, we allow it to clip within the allowed range. Now next is the termination condition. So basically the steps get terminated if the maximum iterations are reached or if the desired fitness threshold is achieved. This is defined by whatever the model is being trained on. If it is not satisfied, it returns back to the step number 2. And if it is satisfied, the program terminates and the global best is found. Finally, we get the output, which is the global best position, and also it represents what is the best objective found by the PSO. Finally, we have the flowchart. The flowchart is a single like how the entire steps in the above like slides consider like how they work around to find the best solution. Next is the working example, including the numerical. So first we take a function fx equals to x square with the minimum set at x equals to 0. We give it a search trend of 0 to 10. The total particles there are 3 with the parameters given as weight equals to 0.5, c1 equals to 1 and c2 equals to 1. Finally, find in the initial values after they are given, we find the calculation which is given as below. We find the we substitute the values and find the velocity. Then we see the new position where it will be by substituting that velocity into the position formula. Afterwards we find the new fitness and then we update the best position accordingly. So for example, if the previous p best was 4 with the fitness equals to 16, the new one will be 2.56 will be which is better. So we're going to assign the new p best as 1.6. Next is the particle 2. So we follow the same steps for that also, and same for the particle 3 as well. We follow the exact same steps and find the new fitness and see if they are changed or not at the end. Then after we are done finding the all the particles new positions or fitness or like the prior ones, we put them inside a table which is the updated one given in the question. Now is the Python implementation of PSO. So first we import the libraries such as NumPy for all the numerical operations and then matplotlib for all the graphs which will be plotted in the following. Then secondly, we initialize all the parameters such as swarm size, bounds, initial positions, velocities, etc. Then we find the velocity equation by implementing the formula we used before for updating particle velocities based on cognitive and social components. Then finally, we loop the iteration over each step so that we can like do it for all the other particles and see if we find any other new values. And then lastly, we just plot the entire graph, helping in visualizing the entire process and displaying the fitness progression and convergence trends over iterations. Following is the code for the entire iteration and algorithm. And finally, we have the PSO convergence curve. It is the graph which shows us how the best fitness goes along with the number of iterations. So we see that the number of iterations spike between 20 to 30, which implements that the best position lies in between that. The following are the applications of PSO. So the first application is neural network training. It uses weights and biases to reduce the overall errors without implementing any gradient, saving us time and also saving us memory. Next is feature selection. It selects the most relevant features which improve the model accuracy and also reduce dimensions. Next is hyperparameter tuning. So PSO basically automatically finds the best parameters for ML models like SVM, RF, or DL. Next is clustering. PSO optimizes cluster centers to produce more accurate clusters than k-means, which is another algorithm used for the same purpose, but PSO is better than that. Next is loss function optimization. So it basically minimizes complex and non-convex loss functions. Next is ensemble optimization. PSO tunes voting weights and model combinations to improve ensemble accuracy. And finally, we have reinforcement learning, which basically gives a reward for all the parameters in order to improve the agent performance. Now we have the advantages of PSO compared to other algorithms. So first is very simple to set up and needs only a small number of parameters. Second, it performs very strongly on non-linear tasks or high dimensional problems, which won't be like as good for other algorithms. Now, third point is that it doesn't depend on any gradient details, which allows it to be handle functions that cannot be differentiated by normal means. Next is the cooperative interaction among particles. It helps to like reach the solutions which are actually good very quickly. Next one is that it is adaptable and can be integrated with the machine learning systems, neural models, or various other techniques. And the final one is that its random exploration also gives a strong ability to search widely and locate global level solutions more quickly. Now, the following are the limitations. The first one being that the method can converge too early when the group loses velocity. Second one, that the result depends very strongly on how the parameters such as weight, C1 and C2 are chosen. If they are not chosen properly, it can also give bad values. Next, that it can be trapped in the local best regions when the search phase is highly complex. And fourth point is that the progress becomes much slower when the problem involves higher dimensions. Fifth one being that it needs like a very thoughtful selection of the swarm size and number of iterations to achieve actual good performance. Now, the following future advancements of PSO are that first of all, the smarter parameter adjustment can help it to tune the inertia along with cognitive and social terms, which can lead to more quicker and stable progress. Second point being blended optimization strategies, which involves merging PSO with methods such as genetic search, etc., which can help create hybrid models which are much stronger than the original one. Third one being handling many goals at once. So advanced form of PSO can also like work around several competing objectives at the same time. It helps in reducing the time and is also very important for complex practical tasks. Fourth point being using in situations that change over time. So PSO can be redesigned to use in the environment that you want it to work in. So it has like it will have a future set of all sort of like systems such as robotics, smart devices, traffic systems, and other things that it can be used inside. Fifth point being the optimizing very large problems like for now the current versions of PSO do not deal with higher data, but in future versions they can also deal with massive amounts of data and higher dimensional machine learning tasks. Sixth point is PSO in parallel environments. So we can use GPUs, cloud platforms, or distributed agents, which can greatly accelerate PSO for industrial level scenarios. Last point being the closer connection with machine learning. As PSO is assisted by very deep models, it can also look for like better models to continue advancing in the future. Final conclusion being that the PSO or particle swarm optimization is a very easy to use and powerful method. It draws inspiration from birds and fishes and how natural swarms occur and how they help each other uh, have more food, or in this case be a more optimized way to solve a task. It also helps by blending individual experiences with wide group information. Its quick convergence and small number of settings help us in being like one of the fastest and able to solve more complex tasks. It is also very helpful as it does not require any gradient, and it can work on better dimensions, or it is able to converge and able to adapt and implement as well. These are the references took for the presentation. And finally, thank you so much.